All right, folks, welcome back. Yeah, this is the continuation of the search code deep dive series. We took a bit of a break over the holidays and then, yeah, I'm back. So I believe where we left off last time, we were in the TransportSearchAction class, specifically in this rather long searchAsyncAction method. So what this method's doing is it's producing the so-called abstract search async action that will execute part of the search request. We talked before a little bit about the search phases, that there can be a can match pre-filter search phase. So this will initially fan out to shards and just say like, oh, do these shards, it asks each, can you possibly return a result for the search request? And so, for example, if you've got a time-based query, the can match pre-filter can look at the current shard and say, oh, everything on this shard is from before this time or after that time. So there's no possible way that I could match anything. So, that's a convenient way of short circuiting, especially if you're fanning out to a lot of indexes. Like if you're doing a log analytics type use case where you're rolling over your log indices every day, say. So, each index corresponds to one day and you're doing a search for a particular week, but you fan out across all your log indexes. Then maybe, if you have, say, a month's worth, anything that's outside of the week that you're filtering on can immediately return and say, yeah, don't bother asking me, with a fairly cheap operation. So down here though was, I believe we were talking about, the typical use case where we're doing a query then fetch. We talked briefly about DFS query then fetch at the end of the last video. So this method, in most cases, will end up returning the search query then fetch async. So the query phase is where it uses Lucene to go through and find the matching documents for the query. Each shard will return its top N matching documents, typically with their scores. And then, so this code here is executing on the coordinator. The individual shards will return their top N with the scores back to the coordinator. The coordinator will collate them, meaning merging them by descending score, and then take the overall top N. And it remembers which shard provided which document. And so it'll go back to those shards and fetch. Fetch means give me back the document source. In theory, you could do this in a single phase where every shard says, oh, here are my top 10 documents and their source. In practice, for a small index, or where you're not fanning out over too many shards, and provide the documents themselves aren't that large, it does result in wasted network bandwidth, wasted serialization and deserialization. Though, to be fair, the document source is not fully deserialized. So mostly it's about moving bytes around within the cluster. So, this two-phased approach does certainly result in a lot fewer bytes. Let's say you have 5 shards, you want the top 10 docs. Each of the 5 shards gives you their top 10. So you've got a total of 50 doc IDs and scores. If they also sent back the source, well, you'd be getting the source for 50 docs. But yeah, really, if you only want to return the top 10, then you can, 40 of those documents are completely useless and have been sent over the wire and just dropped. So yeah, this two-phase approach, yeah, it requires more request response cycles between the coordinator and the data nodes, but generally those are pretty fast. Connections are kept open. And yeah, the two-phase approach probably does make a lot of sense in the vast majority of cases. So this method doesn't actually execute the search async. It just returns the search async. And so if I recall correctly, we were called from this do execute method. And so we've got the execute request where we pass the search async action into execute request. Down here where we actually execute it, I feel like we went through this before. Oh, yes. Yeah, I believe we previously went through this series of listeners, and so we kind of have the async action in our back pocket. That the async action is going to be search, query, then fetch action. Along the way, we do a couple of asynchronous steps. One is we ask search pipeline to transform the request, where if you're not using search pipelines, this is a no-op, and it immediately calls to the listener, where what the listener does is it wraps things up in this rewrite listener, which will then rewrite the search request, which again is also asynchronous, because at least one example of a rewrite that involves an async operation is if you use the terms query with a term lookup. That ends up going and fetching a document from an index, possibly a different index, in order to embed it in the terms query. That, if you say, oh, I don't know the terms that I want to filter on, but if you go and fetch this document from this index and read off the values from this field, that'll tell you the terms. And so because it's making a call potentially to another node to get those terms, we want it to be asynchronous so that you never, ever, ever block on network traffic. And so then, that will invoke that. When the rewrite's done, it calls the rewrite listener, which I think I mentioned last time is badly named. I shouldn't have called it. I did that. I called it a rewrite listener. It's the thing that listens. It doesn't listen and do the rewrite. It listens to the rewrite. And so when the rewrite is complete, invokes this rewrite listener, which eventually, in this build rewrite listener, we've got our search async action provider. And so once the rewrite is complete, end up coming down here and, this again, I believe we looked at this code last time. This is where we evaluate whether we should do cross-cluster search. And so we look at the remote cluster service to say like, hey, remote cluster service, here's the set of indices that are being queried. Can you please tell me which ones are on remote clusters? And in normal searches where you're not doing a remote cluster search or cross cluster search, the set of remote cluster indices is empty. That the remote cluster service may say like, well, it'll say, nope, all of these indices are local. And so we come to execute local search. We have our search async action provider. We call execute search with, now, again, this is where, we could probably just call execute search directly, but if I recall correctly, execute search also gets called by execute remote search. So the fact that we clearly pass through execute local search is probably not such a bad thing, because it does mean that, certainly for those of us who are developers on OpenSearch, getting a stack trace where you can see that it passed through execute local search versus execute remote search, it makes it a lot easier to tell if it's a cross-cluster search or not. Anyway, so here's the execute search method where, because this is where local search and remote search kind of converge, we can have the remote connections. We can have, the remote alias map, remote shard iterators. In practice, for the local search, all of these are going to be empty, null, some combination of them. Like where here in, local search, see, we have an empty list of remote clusters, remote shard iterators, I believe. The function to get connections will just return null. This map down here is the remote alias map. And the one after the listener is, the set of clusters. So, which of course is empty. So here we are in execute search. We can safely ignore all of the remote stuff. The search context, I'm trying to, it's been a while since we looked at this. I believe that, the only time the search context will not be null is if we're doing a point in time search. So with a point in time search, what that does is it sort of establishes, okay, I want to be able to search these shards and get consistent results. I want them frozen in time. I want to be able to send multiple search requests and get the same results. Really, it's a generalization of the old scroll API, because the scroll API would do the same thing, but you could only continue executing the same query to paginate through a large number of results. Point in time is a more powerful version of that, it's the same underlying mechanism that essentially on the shards, they keep a reference to a specific Lucene reader. A Lucene reader is an immutable view over a set of segments. And by incrementing the reference count of an index reader, you also increment the reference count for all of the segments that the reader points to. So even if segment merges happen and segments get deleted, those segments will not, because they're still being referenced by this index reader, and we can continue querying. And that's how point in time search works in a nutshell. We're not going to go into more detail than that today. Instead, we're going to go into this branch where we don't have the search context. So we have to build one. So first step is we need to resolve all of the local indices. Again, because this code could involve cross-cluster search. If it was, the remote clusters would have already resolved things. We don't have to worry about that. We're just going to, resolve all the local indices. So if I recall correctly, this resolve is mostly about, so it delegates out to the index name expression resolver. So, the set of indices could be logging -* to say I want to search all of my logging indices. There may be aliases involved. So the index name expression resolver will go through and, based on the concrete indices, if I recall correctly, it looks for expressions. Well, so all of these, just a specific index name can be an expression, but they can also contain wildcards and stuff. And so, at some point I think it's the expression resolver. So it loops through all of the index expressions, or sorry, it loops through the expression resolvers and asks it to resolve the expressions. Where I suspect, yeah, yeah. Oh, yes. So there are multiple expression resolvers. Yes. Okay. So there's a date math expression resolver and a wildcard expression resolver. So I was talking about the wildcard example of a logging -*. You could also do date math with your indices. So you say, oh, I want indices where the suffix is a date, but a date in the past month, say, which is kind of a cheaper version of that can match logic. So we're down here. So and we look at the metadata. So this metadata is the cluster state metadata. And we have to, within the cluster state, there's this broad metadata. Within the broad metadata, there's the index abstraction metadata, the indices lookup. And so we're going to use these expressions and resolve them back to index abstractions, which could be aliases. And then, based on that, we need to resolve the alias back to, we resolve it back to a right index. Oh, sorry. This is only if we say context.is resolved to right index. Yeah. The normal case, I think, it's down here where we can, if it's an alias or really, I think that's the only way that we could have an index abstraction that points to multiple indices. Because if it's just an index, it'll point to a single index, right? The index abstraction is. So this is where all the resolution of aliases happens if an alias points to multiple indices. Yeah. If there's a data stream then you get the underlying right index for the data stream. Again, if the context is resolve for right index or resolve for right indices index. Yeah, because there's only one. Okay. And then finally, oh, there's a check against system index access. Just make sure, are we allowed to be querying system indices? So, and then finally we convert to an array. Here's where IntelliJ is saying, hey, we don't need to do this. This new index 0, you could just say index.empty array. Now, this is kind of convenient. So, but I'm gonna undo that. But yes, this is something where the old code was allocating a new empty array every time, but we can make that a little bit cheaper. Anyway, let's go back. So we assume that we've now resolved the local indices. So now we have index names. Well, then you need to resolve the search routing. I don't believe this is, so there's this class called operation route. That's where we really resolve things down to search shards. But with this, resolve the search routing if in the expression aliases are used. If expressions point to concrete indices or aliases with no routing defined, the specified routing is used. Okay, so this is taking the set of resolved expressions. If you had an alias pointing to multiple indices, I believe it would have already handled the part where it splits them out. And so each expression here should, I believe, point to a one index, right? That we can guarantee, or at least one index abstraction. And so, yeah, okay. So this is where individual index aliases get resolved. And yeah, so, yep, 2 phases of resolution just for index names. Now, yeah, we copy these into the concrete local indices. So you look to see how many pending search requests are there per node. This will be related to replica selection. So yeah, the node search counts are used as an input to the operation routing. Operation routing is a little bit complicated. It ends up, yeah, it's potentially more complicated than it should be, I guess. I guess it's about as complicated as it needs to be to support everything you can do with routing. So we have the routing map where I believe this map of string to the set of, oh, no. Yeah, sorry. This is the one where, yeah, what's this map that we're returning? Because this is where we iterate through the expression routings. Yeah, this is a little bit odd because I don't really know why we would necessarily need a map. Well, okay. Yeah, it's probably not that important. Okay. But regardless, yep, we have this map. I'm not quite sure why it's a map, but we delegate to the operation routing class to get the set of search shards. And yeah, this is, it'll we have a couple of cases where we'll potentially override the preference. And then, yeah, we get a set of shard iterators. So yeah, this set of shards. Yeah. So we compute the target shards based on the full set of concrete indices. So at this point, we kind of flatten things out. Right. So we may have multiple indices. Each index has potentially multiple shards. But what we return here is a grouped shards iterator. Well, so yeah, I say it's flattened, but it's not totally flattened. If I recall correctly, though, the group shards iterator, it's kind of flattened at the index level, I believe. Yeah. Is it? No, it's actually, it is still, it is grouped at the index level, I believe. And then within it's then subgrouped at the shard level. So for each shard, we have, well, for each shard by like shard number 2, say, we end up pointing to multiple places where we can see those shards. So where were we? We're back in TransportSearchAction. We've gotten the set of search shards. We've got the local shard iterators. Yeah, as a group shards iterator, which we wrap up in these search shard iterators. And then, okay, we have the index routings, I want to get to the point where, so short answer, this is how we're going to figure out which nodes to send the request to for which shard, which incidentally is part of why, I gloss over this, but part of why in the search shards, we did keep track of how many active search requests there are in each node, because that's part of the selection algorithm, right? That it will prefer nodes that aren't handling a lot of search requests. Now we go down here. Oh, I said before, in theory, we can. Oh, no, sorry. This is still true. I was thinking this was query and fetch. Once upon a time, if we go to the definition here, yes, this was finally cleaned up. Once upon a time, there used to be a search type, yes, number 3, that was query and fetch. This, I believe, used to say that, oh, if we only have one shard, then actually we want to do a query and fetch, where it would do it in a single phase. So it would execute the query without returning to the coordinator. It would go ahead and just fetch the result, because if there's only one shard, there's nothing to collate. Yeah. But as part of cleaning up the query and fetch, yeah, it was switched to still do a query then fetch, I guess. Let's go down. Da, da, da. Okay, we've got the whole question of, yeah, okay. I feel like we may have actually gone through some of that stuff before. I hope it wasn't too redundant. Down here is where we actually call the async. Well, we call this this method the search async action provider dot async search action. This is actually where we started the video. It was when we were creating that query then fetch async action. And now we start. So let's go to the query then. Yes. Search query then fetch async action. And we call start on it. Well, start is defined in base class. So the base class, abstract search async action. Okay, so we start. We have a special case for 0 shards, meaning, well, there's nothing to do. Let's just immediately return an empty search response. But we actually care about the more interesting execute phase. So this is still defined in abstract search async action. We do have these OpenTelemetry tracers. So if you enable the OpenTelemetry plugin, then yeah, you can see the start while you have a span for each phase. I haven't seen that in action yet. I'm really looking forward to seeing it in action someday. But yeah, before executing the phase, we can call on phase start, which mostly is just there to let any listeners know this phase is about to start. And then, yeah, if a listener wants to log something, track something, they can. But otherwise, we execute, well, the phase. Oh, sorry. Oh, yeah, because we call it execute phase. Oh, and this is the phase. Yeah, this is where it's a little bit confusing that these async actions are also phases. Yes, search async action extends search phase. We might there might be some opportunity to collapse these into a single class. Yeah, because yeah, I don't recall if there are search phases that are not abstract search async actions. I think they all are. But yeah, we do the record and run. So, okay, this is where we keep track of the start time for overall timing purposes. And then we invoke run. Well, of course, that's inherited from checked runnable. Does abstract search async action define the run, or is that it does? So I wasn't sure if run was where we get to the specific action of the phase. Not yet. Not yet. We're still in the logic that's common to all search phases. So we apparently a search shard iterator can be returned with a skip attribute. Oh, okay. So yeah, this is how the can match logic works. Is that we still have the set of search shard iterators. We don't filter them by the CAD match phase. We just kind of mark them as skippable, I think. So this is where we do that skipping. And, oh, yeah, for historical reasons, because the allow partial search results was added later. It wasn't there right from the beginning. So this was added in to say, yeah, to catch cases where there are code paths that could get you without populating allow partial search result. It defaults to true. I don't necessarily agree with that. I kind of feel like the default behavior should be that if you're missing some shards in your search results, the request should probably fail because, yeah, you should probably know that your results are potentially wrong. And the default behavior should be to error out if your results are potentially wrong. And you should have to explicitly say, no, 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 I'm okay with partial results. But this is what it is that, for historical reasons, allow partial search results defaults to true. And so, yeah, be warned. Sometimes you will get back a successful search response and it may have failed to execute on some shard. But yeah, down here, there is kind of a fail fast, right? So if there are missing shards, not entirely sure what would make a shard be considered missing. So, okay, so it iterates through all of the shard iterators. Yeah. Yeah, I'm not entirely sure why. Yeah, I guess maybe the operation routing will only return shards that it knows exist. Oh, no, sorry. Yeah. Yes, it may return a routing for a shard that is empty. So it's saying, like, I guess maybe if you specified a preference for replicas only and you're hitting an index that doesn't have any replicas, and so there were only primaries. And so, yeah, that could be a way that you could end up with a search shard iterator that for a given shard didn't, that it wasn't able to resolve something according to the preference specified. Anyway, yeah. So now it just iterates through all the shards and calls perform phase on shard. Now remember, we're still on the coordinator at this point. So we're not actually performing the phase per se. We're going to dispatch the request. So I guess you could call this dispatch phase 2 shard, might be a clearer name. But yeah. Yeah, this one down here, execute phase on shard, is probably getting a little bit closer. Again, I kind of like the idea of throwing the word dispatch in just to suggest this. Like, no, we're not on the data node with the shard yet. We're actually just gonna, fire off the request. So yeah, we create a runnable, which I think down here we're gonna, yeah. So if we're throttling, we're going to try to run it. But if we're not, we're just going to straight up and run it. And so what the runnable does is, so it's going to call this execute phase on shard, and it's going to have a listener, right? So keep in mind that we're going to fan out to a bunch of shards. So, each time this method's called, it's going to kick off. Well, wait, actually, when we call r.run, aren't we running it on the current thread? That doesn't seem right. How do we fan it out on the, sorry, I'm going to try to find the place where, yeah, because this would just do things sequentially, wouldn't it? Right? Like it would just say like, oh, I've got a runnable, I'm going to run it. But we should probably be handing it off to an executor. Yeah, because we want to search all of the, yeah, we want to search all of the requests in, or, oh, you know what? I bet that's it. I bet that the fact that it's wrapped up in a runnable, yeah, isn't that exciting, I guess. I think, yeah, the part where we hand it off to an executor, I bet, yeah, that's why this is called execute, because it probably makes use of the executor. So yeah, this is the one. the execute phase on shard, and this is where we start to get phase specific. So in the case of doing a query phase, right? Because we're going to do the query phase and then we're going to do the fetch phase. So yeah, the execution. So this is still on the coordinator's request thread. So we do another rewrite. Now, the funny thing is, it's like, hey, didn't we already do a rewrite? It's like, well, yes, but that was the coordinator level search request. At this point, what we do is we convert the coordinator level search request into a shard level search request. See, so this is of type shard search request. Now, the shard level search request contains the coordinator level search request, which was the thing that we deserialized from the REST search action all the way back in episode 1. But yeah, the shard search request ends up containing like, okay, well, here's the routing info. We do pass along information about like, oh, by the way, here's the total number of shards. I don't recall why that's relevant to the shard search request, but it has that information. This shard search request is the thing that's going to get serialized and sent from the coordinator to the data node. So yeah, there's a search request rewrite, but then also the shard search request. In practice, this rewrite is actually not very interesting. Mostly, for example, it's copying. It does a shallow copy of the this is just if we want to disable track and total hits. Yeah, no, this isn't actually a very interesting rewrite. It's not nearly as complex as the other rewrite. So yeah, it's just kind of tweaking the shard level request. Yeah. Here's where we can, we get the search transport. So at this point, we're getting, well, the search transport service has the node client. If you followed the indexing series, when we got from the coordinator to a data node on the indexing side, I did do a little bit of a deep dive there into, we have these transport services. The transport services wrap a node client. The node client tends to execute these node to node calls via whatever transport we're using. I believe it's now almost entirely a netty transport, but it can be, a netty transport wrapped in a security transport, which does checks to make sure that this request is allowed under the current, running context, which is based on who's making the call. We do additional checks to make sure that the request is allowed to go. And so we've got our shard level result listener. So this listener here is the one that's going to listen for the results from this shard. And yeah, so the send execute query, mostly it's, transport service, send child request. So, we have, the current parent task. And so we end up producing a subtask of the parent task. This is useful if you want to look at the task management APIs and see how long a task's been running for, what child tasks exist under an existing task. So, because of course these tasks can span multiple nodes, like the coordinator and the data nodes. So, yeah, before we get into what happens on the data node, let's take a quick step back and look at where we called execute phase on shard. So when the shard's results are ready, so this is when that call out to the individual shard has returned. We call this on shard result, where we have some, abstract result type, that ends up being phase dependent. So the assumption is, so we have our results plural, which is of type search phase results plural, that consumes a result. You can also notify, another listener to say like, the results were consumed. Actually, no, this is not an async listener. This is, this is just sort of saying like, once I've consumed my results, I just want to, have some counters and stuff. The search phase results for the query phase. So let's look at the search phase results. So this is an abstract class, and yeah, query phase result consumer is the implementation of search phase results that we're doing on the query side. So we call this consume result. So mostly all that we do here, so we've got a super consume result, which basically, yeah, so it uses this atomic array. I think we've talked a little bit about these atomic arrays before that, yeah, they basically guarantee that, yeah, when we insert into this array, like this could just be a plain old Java array, but we would definitely need to make sure that before we finally read back the value, yeah, that everything's populated. So each thread could be inserting into its position in an array, but yeah, you want to make sure that the last thread is able to see all of the results. Anyway, yeah. So the next thing to do upon consuming a query phase result is nothing. But yeah, I recall, yeah, eventually we're going to want to call this reduce. So mostly what we're doing is we get all of the results back from each shard, kind of stash them in this array. And then once the last result comes in, that's where we're going to call this reduce method. I believe that was back. Okay, so we do this on shard result. Yeah, I don't recall actually when possibly in the on shard. So there was a listener here for the consume result. It may be in the on shard result consume at some point. Nope. No. This is one that's just kind of keeping track of successful operations. Okay, so there is this on phase done. Is this the one? So this is when we want to transition from one search phase to the next, and we call execute next phase. But what I want to see is where do we call, well, actually, what I should have done, we know that before we transition from the query phase to the fetch phase, we have to call reduce. So this is that method. I talked about the collation. If you're talking about if you're just focused on top hits, yeah, we have this pending merges, we consume the top docs, and yeah, we end up getting, the final top of the top docs. Each shard has returned its top documents. And so, yeah, I believe it's this consume top docs. Yeah, that ends up doing the merge oh, sorry, no, this is still a list of top docs. Yeah, so we have to, yeah, okay, here where we call controller doc reduce query phase or reduce diff query phase. But yeah, this is one I think that ends up, where do we process the top docs list? The buffered top docs. So I'm highlighting it so that I could see uses. Actually, I should just command click on it. Where's this guy used? Okay. Sorted top docs. Okay. So we end up doing this, sorting. So here's where we do the collation. And yeah, we specify the from and the size. And yeah. So yeah, this sort docs, I believe, is the thing that ends up collating and eventually truncating, probably. Right? Because we would use the size to say, okay, so yeah, here, merge top docs. Okay. Yep. Cool. Yeah. So that's where that collation happens. Obviously, you can have more than just top docs. You can also have aggregations. So we've got an aggregation reduce context builder because different aggregations may have different ways of being merged. For example, if you have a metric aggregation on, this doing a max function, the way that you would merge is you look at, results and you take the maximum. If you have a sum metric, you would gather up the individual shard results and you would sum them up. Again, kind of grouping the aggregations by their respective buckets. So cool. Oh yeah. And then there's also, yeah, suggestions. If there is a suggest that we can send back, saying like, oh, actually, would you like to maybe run this query, next, as, possible additional, yeah, or sorry, like a did you mean blah. That's what that, sometimes if you enable suggest, maybe you don't get back a lot of search hits, but it can respond with, did you mean to ask me for blah? Because I found this similarly spelled word that actually does have more hits. Cool. So we started to get a little bit into processing the results of each shard query phase. But, do I want to leave it there, or do I want to dive a little bit into, I think next time, let me just kind of close the loop a little bit. We were in the search then fetch async action. We called get search transport. We called execute, send execute query. So an important thing is that any transport action, it sends a serialized request where we've gone through this before, either in the indexing series or earlier in the search series. And oh, sorry. Oh, interesting. There is actually something here where we do still do a query and fetch, but it doesn't exist anymore. Okay, cool. So we do actually collapse query and fetch into a single operation. Cool. Okay. But we do it here, not based on the search type. So you can't actually specify the search type anymore. But we do have the optimization that, if you're only hitting one shard, then you're only, you could query and fetch in a single call. Anyway, so getting back to the transport action, when we send a transport call from one node to another, we have to specify an action name. And that is what, on the receiving end, it'll know, okay, I have a request, I have a task that's associated, that's a task on the remote node. Like it'll create a new child task at its end. Like the receiving node will create a child task, but it needs to know which action do I dispatch this to. And so that's based on the query action name. So we see this is the full thing here is indices data read search phase / query. And you can look at other phases. There is, okay, this is query plus fetch for a scroll. Yeah. Yeah, I guess for a scroll, it still does make sense to do a query and fetch, probably. So the query action though, this is associated with, oh, sorry, I want to find one of these. No, this is where we're sending the request. Where do we actually have it registered? Okay, sorry. Yeah, we have a channel. Ah, yes. Okay, here it is. So when the search transport service starts up, so the search, this is where I find this very confusing. So we use the search transport service on the coordinator to send the query action to the data node. And then on the data node, we also have a search transport service, which has a request handler, which, given the query action name, knows to hand it off to, this operation. Like this is the action, or this is the request handler, right? That it says search service dot execute query phase. So I think I'm just going to very gently click into this, and we're probably going to stop here because we've now landed on the data node. We're about to search a shard on the data node. And next time, we should be able to get into what, where we actually start calling to Lucene for the search. Can we get into that? Probably. We could probably get into that. There are a couple more layers we have to get down through. But we'll first have to start off with the fact that there's another rewrite. So we rewrote the top level search request on the coordinator right after running through search pipelines. Well, the request transform side of a search pipeline. And we can also transform the request at the shard level. We'll look at what that means a little bit next time. Okay. Thank you very much for listening, and we'll be back.